Hey guys, today we'll be going through Module 1 of HSC Preliminary Physics, which is kinematics. A quick disclaimer before I begin this video. My explanations are a recount of my own personal learning, and it's used as a summary of the topics in a way that I understand. So if I get anything wrong, or if I miss any topics, feel free to clarify or correct me in the comment section. Before we get to theory, it's important to familiarize ourselves with the SI units, which are the System International Units. These are the base universally used units which are used to quantify the measurements we have in physics. So, why are these units important? These units are important because they set a specific scale and measurement for the values we use in physics and also daily life, such as length, time, mass, and more. So, the base values that are used as in the SI units are these values. So, length, which is measured in meters as seen here, mass, which is measured in kilograms with the symbol of kg, time in seconds with the symbol of S, electric current in amperes with a capital letter A as its unit symbol, temperature in Kelvin with a unit symbol of K, luminous intensity, which is measured in candelars with a unit symbol of CD, and amount of substance, which is measured in moles with just a symbol of mole, which you'll see in chemistry. So, some important things to note before we move on. Because these are the base units, if you see, for example, let's say time, if you see time measured in minutes, it is important to convert into seconds because these base units must be used when you're calculating in physics. So if you get, like, for example, 2 minutes, then you would have to do 60 seconds per minute. So you would get 120 seconds instead of using 2 minutes. Furthermore, just to clear up anything, Kelvin is used in the same scale as Celsius. So, for example, if I was to say you increase the temperature by 1 Kelvin, that would be the same as increasing the temperature by 1 Celsius because not 1 Kelvin is equal to 1 Celsius, but the scale is the same. So, what are metric prefixes? Another thing we need to know are metric prefixes. Essentially, these are the prefixes that may show up in front of your measuring units in order to make it a readable format. You may have heard of some of these values before, which is in here, this section here. So, basically what they do is they increase the values or decrease the values by timesing it by a power of 10. So the ones we go below here, the ones that we need to memorize in physics are tera, which is 10 to the power of 12, giga, 10 to the power of 9, mega, 10 to the power of 6, kilo, 10 to the power of 3, and the base unit, which is 10 to the power of 0. This is essentially just timesing the value by 1 because nothing changes. Deci, which is 10 to the power of -1, so you're dividing it by 10. Centi, which is 10 to the power of -2, which means you're dividing it by 10 to the power of 2, so dividing it by 100. Milli, which is 10 to the power of 3. Micro, which is 10 to the power of -6. And this is in mu, but later on when we go to Module 2 for physics, this symbol is not to be confused with the frictional coefficient. It's not this. And nano, which is 10 to the -9. You may have seen some of these values before, so like kilo, maybe like centi, milli, maybe micro. So basically, what we do is, essentially, if we have like kilogram, that's like 10 to the 3 times gram, right? Because gram, it's not the SI unit, but it's the base unit. So if we get kilogram, if we add it there, then that's, give me a second, kilogram, then that means that's 1 gram times 10 to the power of 3. So that's 1,000 grams. Okay, so let's jump into the content. In physics, there are 2 major types of quantities, scalar and vector quantities. Scalar quantities are quantities that have only a magnitude. However, vector quantities are quantities that have both a magnitude and a direction. For example, let's go on to the next page. Say we have distance. Distance is a scalar quantity, which means it only has a magnitude. Let's say we have a distance of 5 meters. However, if we have displacement, then we need to ask ourselves, where is the 5 meters in the direction of? Are we going 5 meters upwards? 5 meters to the east? 5 meters to the west? Or 5 meters south? So this is an example of displacement, which is a vector quantity. So it has a magnitude and a direction. Basically, for a vector quantity, we must state the magnitude. We must state the magnitude, which is here, the unit, and also the direction. So for example, let's just say Bobby walks like 5 meters to the east. So we must write 5 meters east. Whereas for distance, we just have to write 5 meters. Okay, so let's go back. Vector quantities can be represented using arrows. So when we represent vector quantities using arrows, the size of the vector is depicted by the length of the arrow. So the longer the length of the arrow, so this bit here, the larger the vector is. So for example, if we had like 1 meter as a vector quantity, it would be something like this. But if we had 5 meters, this would be, give me a second. This would be 1 meter, and this would be like 5 meters. As you can see, the larger value, which is over there, has a larger size of the arrow. And then the arrowhead is at the very end of the line. And the arrowhead essentially points to the direction that the vector quantity is moving in, or the direction of the vector quantity that it's going in. So earlier I mentioned distance versus displacement. So I said distance is a scalar quantity, which means it only has magnitude. Distance refers to how much the object has traveled from its original position. Displacement, the vector quantity, has a magnitude and a direction. And this basically refers to how far its final position is from its initial position. So we have an example of the two below. Final distance equals z plus y, because the person moved from here to here. So the distance they traveled is the sum of those two sides. Meanwhile, the displacement is the length from the final to the original. So it would just be the length of x over here. Another example we can see is over here. So let's say there's a fly here that flies like this length. So its distance would be this, because the object, the fly, has traveled that much. However, its initial is here and its final is here, which means its displacement is going to be this length. Now we can move on to velocity and speed. So speed, we've all heard of speed before. Speed is the measurement of distance over time. So the distance traveled by the object, which let's just say here, so this over the time it takes, the time taken to travel that distance. Meanwhile, velocity is the measurement of displacement over time. So the original from the final once again, and the time it takes to get to that point. Because displacement is a vector quantity, that means velocity is also going to be a vector quantity. The units for both of these are meters per second, and this can be derived through these are not called SI units, sorry. These are derived from SI units. They can be derived from the values that make up the value. So for example, speed equals distance over time. We know that in physics, distance is measured in meters and time is measured in seconds. So speed is every meter per second. So we get meters per second as the final value. So we can move on. Sorry, I previously forgot to mention, we can calculate average velocity and average speed by doing the total distance / displacement over the change in time. Because objects can have different speeds or different velocities at different points in time. But to find the average, it's just the total distance or displacement over the total time. Okay, so before we move on to acceleration, let's have a go at converting units of speed and velocity. So let's say we get a speed, for example, in the format of 60 kilometers per hour. Now, we know that the unit for speed is meters per second, right? So, how do we convert this into meters per second? We know that 1 kilometer is equal to 10 to the power of 3 meters. And we know that 1 hour equals 60 minutes equals 60 times 60 seconds, because there's 60 minutes in an hour and 60 seconds in a minute. So if we convert it, we get 60 times 10 to the power of 3 meters per 60 squared seconds. We need to do this because we need to get these units into the format of this. So let's sub that into a calculator. 60 times 10 to the power of 3 divided by 60 squared. Then we get 16.66 to infinity meters per second. Or if you want to round to significant figures, because we got 2 significant figures, we can get round about 17 meters per second. Also, whenever you're using units, it's better to depict it as such, like that. This is because we don't like having fractions in our units. Okay, so now that we've covered how to convert units and also what a scalar vector is and also what velocity is, we can go through acceleration. So, what is acceleration? Acceleration is the measurement of a change in velocity of an object over the change in time. So this is, as I said before, this is a measurement of how much the velocity of an object is changing. In a mathematical depiction, it is seen as A equals change in v over t, where A equals acceleration, v equals velocity, and t equals time. Or if we put it, we can also depict change in velocity as v final minus v initial. So the final velocity minus the initial velocity over time. Because A is the change of a vector quantity over a scalar quantity, acceleration is also a vector quantity. Furthermore, we can derive the units for acceleration because we know that the units for velocity equals meters per second, and we know that this is over time, which is in seconds. So if we get meters per second, we get meters on second squared, or meters second to the power of -2. So that's essentially the unit for acceleration. Because we got the mathematical equation A equals v minus u on t, where t is time, u is initial velocity, or u can also be similarly depicted as vi, where I is initial, but I'm just going to use u. And v is the final velocity, which can also be depicted as VF, V final. Then acceleration, which is in the units of ms meters. Yeah. Okay. So because we got this equation, we can now use it to solve some equations. This is also a kinematic equation, but because we haven't gone through kinematics yet, I'm just going to leave that for next time. So we can first try a practice question. A car starts from rest and reaches a velocity of 20 meters per second due east in 5 seconds. What is its average acceleration? So let me just write that down. Whenever we start a question like this, we always want to start with a table of values. So what do we know? I've said previously that the car started from rest. If it starts from rest, then that means it's not moving. That means its initial velocity will have to be 0 meters per second. It says it reaches a velocity of 20 meters per second, which means its final velocity would have to be 20 meters per second. And then I said the time taken for it to achieve this was 5 seconds. So t equals 5 seconds. And this is all in the direction of east. And when we do this, we're going to define east as positive. So east is positive. And then now that we have these values, all we need to do is we just plug it into the mathematical equation we got. So 20, which is our final velocity, 20 minus 0, which is our initial, over 5, which is our time, equals 20 on 5, which also equals 4 meters per second squared. And that's how we derive it. And recall that acceleration is a vector quantity, which means whenever we finish this, we need to add a direction at the end. So we must say east.